The monotone algorithm for the job scheduling problem. Note that we understand the exact form of an implementable algorithm. We can construct the one that approximates the optimal outcome. In fact, the optimal itself is implementable. Since it can satisfy weak monotonicity, see the exercises for more details. But the computation of the optimal outcome is a bit hard. We wish to construct efficiently computable mechanisms, and hence design a monotone and polynomial time approximation algorithm. Note that we face a classic algorithmic problem. No game theoretic issues are left for us to handle. Before we start, let us assume that jobs and machines are reordered so that S1 is greater than or equals to S2, which is greater than or equals to S3, and so on, which is greater than or equals to Sm. And P1, which is greater than or equals to P2, which is greater than or equals to P3, and so on, which is greater than or equals to Pn. For the algorithmic construction, we first need to estimate the optimal makespan of a given instance. Estimating the optimal makespan. Fix a job index j and some target makespan t. If a schedule has makespan at most t, then it must assign any job out of 1, 2, 3 until j to a machine I such that t is greater than or equals to pj over si. Let I of jt equals to the maxima of the set of I such that t is greater than or equals to pj over si. Thus, any schedule with maxspan at most t assigns jobs 1 to 3 until j to machines 1 to 3 until I of jt. By definition, from space consideration, it immediately follows that t is greater than or equals to the summations of pk summing with index k starting from 1 to j over the summations of sl summing with index l starting from 1 to I of jt. Now define that tj equals to min max, where the minima is taken among all possible index I, and the maxima is taken among two terms. The first term is pj over si. The second term is the summations of pk summing with index k starting from 1 to j over the summations of sl summing with index l starting from 1 to I. Lemma 12.3. For any job index j, the optimal makespan is at least tj. Proof: fix any t which is less than tj. We prove that t violates 12.1, hence cannot be any feasible makespan, and the claim follows. Let ij be the index that determines tj. The left expression in the max term is increasing with I, while the right term is decreasing. Thus ij is either the last I, where the right term is larger than the left one, or the first I, for which the left term is larger than the right one. We prove that t violates 12.1 for each case separately. Case 1. The summations of pk summing with index k starting from 1 to j over the summations of sl summing with index l starting from 1 to ij, which is greater than or equals to pj over sij. For ij plus 1, the max term is received by pj over sij plus 1. Since tj is the min-max, we get tj is less than or equals to pj over sij plus 1. And since t is less than tj, we have that I of jt is less than or equals to ij, and t is less than tj, which is by definition is equals to the summations of pk summing with the index k starting from 1 to j over the summations of sl summing with index l starting from 1 to ij, which is less than or equals to the summations of pk summing with index k starting from 1 to j over the summations of sl starting from l equals to 1 until L equals to I of JT. So hence T violates 12.1 as claimed. Case 2. The opposite. The summations of pk summing with index k starting from 1 to j over the summations of SL starting from L equals to 1 to L equals to ij, which is less than pj over sij. The case is that tj, which is less than equals to summations of pk summing with index k starting from 1 to j over the summations of SL summing with index L starting from 1 to ij minus 1. Since tj is the min-max. And the max for ij minus 1 is received at the right. In addition, I of jt is less than ij since tj equals to pj over sij and t is less than tj. Thus, t is less than tj, which is less than equals to the summations of pk summing with index k starting from 1 to j over the summations of SL summing with index L starting from 1 to ij minus 1, which is less than equals to the summations of pk summing with index k starting from 1 to j over the summations of si summing with SL summing with index L starting from 1 to I of jt as we need. With this, we get a good lower bound estimate of the optimal makespan. TLB equals to the maxima j of tj. The optimal makespan is at least tj for any j, hence it is at least TLB. A fractional algorithm. We start with a fractional schedule. If a machine I gets an alpha fraction of a job j, then the resulting load is assumed to be alpha times pj over si. This is of course not a valid schedule, and we later route it to an integral one. Definition 12.4. The fractional allocation. Let j be the first job such that the summations of pk, summing with index k starting from 1 to j, which is greater than TLB, times SL, times S1, assign to machine 1, jobs 1 to 3 until j minus 1, plus a fraction of j in order to equate L1 equals to TLB times S1. Continue recursively with the assigned fractions of jobs and with the machines 2 to 3, 2, 3, 4 until m. Lemma 12.5. There is enough space to fractional assign all jobs, and if a job j is fractionally assigned to machine I, then pj over si is less than equals to TLB. Proof. Let ij be the index that determines tj. Since TLB is greater than equals to tj, which is greater than equals to the summations of pk summing with index k starting from 1 to j over the summations of SL summing with the index L starting from 1 to ij, we can fractionally assign jobs 1 to 3 until j up to machine ij. Since tj is greater than equals to pj over sij, we get the second part of the claim, and the setting j equals to n gives the first part. Lemma 12.6. The fractional load function is monotone. Proof. We show that if si increases to si prime equals to alpha times si for alpha greater than 1, then li prime, which is less than equals to li. Let TLB prime denote the new estimate of the optimal makespan. We first claim that TLB prime is less than equals to alpha times TLB. For an instance, Si prime prime, S2 prime prime, S1 prime prime, S2 prime prime, and so on to Sn prime prime, such that SL prime prime equals to alpha times SL for all machines L, we have that TLB prime prime equals to alpha times TLB, since both terms in the max expression of Tj were multiplied by alpha. Since SL prime is less than equals to SL For OL, we have that TLB prime is less than or equals to TLB prime prime. Now, if Li equals to TLB times Si, i.e. I was full, then Li prime is less than or equals to TLB prime times Si prime, which is less than or equals to TLB times Si, which is equals to Li. Otherwise, Li is less than TLB times Si, hence I is the last non-empty machine. Since TLB prime is greater than or equals to TLB, all previous machines now get at least the same load as before, hence machine I cannot get more load. We now route to an integral schedule. The natural routing of integrally placing each job on one of the machines that got some fraction of it provides a two approximation but violates the required monotonicity. See the exercises. We offer two types of routing, a randomized routing and a deterministic one. The former is simpler and results in a better approximation ratio, but uses the weaker solution concept of truthfulness in expectation. The latter is slightly more involved and uses a deterministic truthfulness, but results in an inferior approximation ratio. Definition 12.7, a randomized routing. Choose alpha, which is in the closed interval between 0 and 1, uniformly, at random, for every job j that was fractionally assigned to I and I plus 1. If j's fraction on I is at least alpha, assign j to I in full. Otherwise, assign j to I plus 1. Theorem 12.8. The randomized scheduling algorithm is truthful in expectation and obtains a true approximation to the optimal makespan in polynomial time. Proof. Let us check the approximation first. The machine I may get, in addition to its full jobs, two more jobs. One, J, is shared with machine I minus 1, and the other, K, is shared with machine I plus 1. If j was rounded to I, then I initially has at least 1 minus alpha fraction of j, hence the additional load caused by j is at most alpha times pj. Similarly, if k was rounded to I, then I initially has at least alpha fraction of k. Hence, the additional load caused by k is at most 1 minus alpha times pk. Thus, the maximum total additional load that I get is alpha times pj plus 1 minus alpha times pk. By lemma 12.5, we have that the maxima chosen among the pj or pk is less than or equals to tlb, and since tlb is not larger than the optimal maximal makespan, the approximation claim follows. For truthfulness, we only need that the expected load is monotone. Note that machine I-1 gets job j with a probability alpha, so I gets it with a probability 1 minus alpha. And I gets k with probability alpha. So the expected load of a machine I is exactly its fractional load. The claim now follows from lemma 12.6. An integral deterministic algorithm. To be accurate, what follows is not exactly a routing of the fractional assignment we obtained above, but a similar in spirit deterministic assignment. We set virtual speeds where the fastest machine is set to be slightly faster, and the others are set to be slightly slower. We find a fractional assignment according to these virtual speeds, and then use the natural routing of placing each job fully on the first machine it is fractionally assigned to. With these virtual speeds, routing that previously failed to be monotone now succeeds. Definition 12.9. A deterministic algorithm. Given the bits S1, S2, and so on to Sm, perform the following. 1. Set new virtual speeds d1, d2, d3 until dm as follows. Let d1 equals to 8 over 5 times s1, and for I which is greater than equals to 2, let di be the closest value of the breakpoints s1 over 2 to the I 2.5 to the I, for I equals to 1 to 3 until 5, and so on, such that di is less than equals to si. 2. Compute TLB according to the virtual speeds, i.e. TLB equals to TLB of did minus I. 3. Assign jobs to machines starting from the largest job and the fastest machine. Move to the next machine when the current machine I holds jobs with total processing time larger or equal to TLB times DI. Note that if the fastest machine changes its speed, then all the DIs may change. Also note that step 3 manages to assign all jobs, since what we are doing is exactly the deterministic natural routing described above for the fractional assignment, using the DIs instead of the SIs. As we shall see, this crucial difference enables a monotonicity in the cost of a certain loss in the approximation. To exactly see the approximation loss, first note that TLB of D is less than or equals to 2.5 times TLB of S, since the speeds are made slower by at most this factor. For the fastest machine, since S1 is lower than D1, the actual load up to TLB of D may be 1.6 times TLB of D, which is less than or equals to 4 times TLB over S. As we may integrally place on machine 1 one job that is partially assigned also to machine 2, observe 1 that D1 is greater than or equals to 4D2, and 2, by the fractional rules, the added job has load at most TLB of D times D2. Thus, get that the load on machine 1 is at most 5 over 4 times 1.6 times TLB of G, which is less than or equals to 5 times TLB of S. For any other machine, DI is less than or equals to SI, and so after we integrally place the one extra partial job, the load can be at most 2 times TLB of D times DI, which is less than or equals to 2 times 2.5 times TLB of S times SI, which is equals to 5 times TLB of S times SI. Since TLB of S lower bounds the optimal make span, for S, the approximation follows. To understand why monotonicity holds, we first need few observations that easily follow from our knowledge on the fractional assignment. For any I which is greater than 1 and beta is less than di, TLB of beta d minus I is less than or equals to 5 over 4 times TLB of did minus I. Consider the following modification to the fractional assignment for did minus I. Machine I does not get any job, and each machine 1 less than or equals to I prime less than I gets the jobs that were previously assigned to machine I prime plus 1. Since I prime is faster than I prime plus 1, any machine 2 less than or equals to I prime less than I does not cross the TLB of did minus I limit. As for machine 1, note that it is always the case that D1 is greater than or equals to 4 times D2, Hence, the new load on machine 1 is at most 5 over 4 times TLB of dId minus I. If a machine I greater than 1 slows down, then the total work assigned to the faster machines does not decrease, which follows immediately from the fact that TLB of di prime d minus I is greater than or equals to TLB of dId minus I. For di prime which is greater than or equals to di. If the fastest machine slows down, yet remains the fastest, then its assigned work does not increase. Let S1 prime equals to C times S1 for some C which is less than 1. Therefore, all breakpoints shift by a factor of C. If no speed Si moves to a new breakpoint, then all D's move by a factor of C. The resulting TLB will therefore also move by a factor of C, meaning that machine 1 will get the same set of jobs as before. If additionally some SIs move to a new breakpoint, this implies that the respective DIs decrease. And by the monotonicity of TLB, it also decreases, which means that machine 1 will not get more work. Lemma 12.10. The deterministic algorithm is monotone. Proof. Suppose that machine I slows down from Si to Si prime, which is less than Si. We need to show that it does not get more work. Assume that the vector D has indeed changed because of I's change. If I is the fastest machine and it remains the fastest, then the above observation is what we need. If the fastest machine changes to I prime, then we add an artificial breakpoint to the slowdown decrease, where I and I prime speeds are identical, and the title of the fastest machine moves from I to I prime. Note that the same threshold t is computed when the title goes from I to I prime. I's work, when it is the fastest machine, is at least 8 over 5 times S I times t, while I's work, when I prime is the fastest, is at most 2 times S1 over 2.5 times t, which is less than 8 over 5 times Si times t, hence decreases. If I is not the fastest, but still full, then di prime is less than di, since the breakpoints remain fixed, and therefore TLB of di prime d minus I is less than or equals to 5 over 4 times TLB of di d minus I, with Si I prime's work with I's work is at least t times di, where t equals to TLB of dId minus I, and with Si prime, its work is at most 2 times 5 over 4 times t times di over 2.5, which equals to t times di. Hence, I's load does not increase. Finally, note that if I is not full, then by the third observation, since the work of the previous machines does not decrease, then I's work does not increase. By the above arguments, we immediately get the following theorem. Theorem 12.11. There exists a truthful deterministic mechanism for scheduling related machines that approximates the make span by a factor of 5. A note about price computation is in place. A polynomial time mechanism must compute the prices in polynomial time To compute the prices for both the randomized and the deterministic mechanisms, we need to integrate over the load function of a player fixing the other's speeds. In both cases, this is a step function with polynomial number of steps. When a player declares a large enough speed, she will get full jobs. She will get all jobs, and as she decreases her speed, more and more jobs will be assigned elsewhere, where the set of assigned jobs will decrease monotonically. Thus, we can see that price computation is polynomial time. Without the monotonicity requirement, a pitas for related machine exists. The question whether one can incorporate truthfulness is still open. Open question. Does there exist a truthful pitas for related machines? The technical discussion of this section aims to demonstrate that for single-dimensional domains, the algorithmic implications of the game theoretical requirement are manageable and leave ample flexibility for the algorithmic designer. Multidimensionality, on the other hand, does not exhibit this easy structure, and the rest of this chapter is concerned with exactly this issue.